Okay, hello, good morning, afternoon, or evening. I don't know when will you be watching this. But well, my name is Leonardo Ramirez Cabrera, and let us go through our argumentative exam for the model processing using linear algebra subject, which was actually a really nice subject. I enjoyed it really much. And well, it actually gave me the tools in order to see how linear algebra can be something really relevant in our daily lives, even when we think linear algebra is just kind of using numbers and numerical methods and whatever. First of all, I want to apologize because of the outside noise. That's kind of not on my control. Apparently, people are celebrating, Mexico's independence or whatever. But well, they probably have the whole puente, so they are not really that worried about anything. But well, let's first go through our instructions. We are in a semiconductor company and we have to design a quantum well optoelectronic device. In order to, well, kind of do this, we have to get calculations for a device that should emit light at a specific wavelength or, well, in simple terms, just a color. We will be choosing the red one for convenience and because we also want this to be as realistic as possible. So, well, my IQ told me that red was kind of the easiest one or the most realistic one, or the one that we see most commonly on daily life appliances. So let's start as seen in the technical content requirements from the time independent Schrödinger equation, which is shown into here. Well, we have this equation. We also have to take into account the different variables that it has. The h bar, which is the reduced Planck's constant, which is just a numerical value. We will get this later. The mass of the particle, of course, as in here in m, and the wave function, which is shown with the Greek letter psi. And well, let's first kind of understand what a quantum well is. It in Spanish is a pozo cuántico. So, well, we all, of course, have these kind of borders of the quantum well, which will be shown with zero, of course, because this is zero in X, and will end up in A. So that will be the interval we will be working with. And well, of course, in order to make this kind of a mathematical overview that we are already kind of experts in, let's say, we can divide this in little subintervals that are equally spaced. Of course, these are like massively little in order so that we can compute this in the most precise way possible. And we will be seeing this with delta x. So delta x, of course, is this total width, which is a divided by n plus 1, which is the kind of, let's say, number of equally spaced subintervals. So, well, in order to get kind of a solution, we have to introduce the central finite difference approximations. Let's remember that we have different finite differences, like the forward or the backwards, but we are going to focus on the central because this method ends up with an eigenvector eigenvalue problem, which we can solve in order to get the eigenvalues, which in this specific context will give us the energy levels. And that's kind of important because we want to get those energy levels for our, sorry about that. I don't know what's going on with my computer. This kind of energy levels, which is signalized as E1, E2, E3. But that's kind of the main objective. So we have this equivalence that was given to us during lectures, which is the partial second derivative order kind of equivalence of the wavelength function. It's important to just let everyone know that this is kind of the main thing of this formula, but we have some other values that will be negligible due to how small they are or how close they are to zero. And well, that just makes this easier because if we take into account all of those values, well, we are just basically committing suicide, and this will be kind of more difficult. So we replace that specific value in our equation one, which is the time independent Schrödinger equation. So we will end up with this. Of course, this tends to zero. We just kind of replace things. And We also group our constants and we got to this already. It is important to kind of, with our engineering eye, to see how we do not like this minus or negative sign in there. So we're gonna just apply this negative sign into this in order so that it's way easier. As seen in here, we already kind of got rid of this minus symbol. We put it into here. So now what happens next is going to be absolutely beautiful. But first, we have to talk about boundary conditions. In some other lectures with Momox, we got some other type of conditions, which were given for other type of problems in electromagnetism, in electric systems, in thermodynamics, sorry. But here we have boundary conditions due to the nature of a quantum well. Of course, well, the quantum well is kind of delimited by these two borders. So let's account for those borders and our conditions. Of course, whenever the value of kind of this x axis is in zero, of course, that's pretty trivial, it's zero, but also in A, because, well, that's where our quantum well is ending. So makes sense. And well, when do we have A in our quantum well? Of course, when the n value is equal to n plus 1. Of course, we also have the zero, because as we said, that's kind of trivial, so there's no problem in understanding that. So let us continue. Well, of course, I can be whatever designated number we choose. Of course, for convenience, let's choose 1, 2, 3, 4, 5. Why not choosing 0? Because it doesn't make sense, because 0 is already given into a boundary condition, as in here. So that makes no sense. So following the formula I minus 1, then 2i, well, 2 psi I, and then psi I plus 1, of course minus, we end up with this. And as we can see, it's actually funny how we are kind of repeating the same coefficients, right? So here we have a minus 1, here we have a 2, and here we have a minus 1. And that's how basically we end up with a three-diagonal matrix, which will be seen here below. Here we are. We have, of course, this value, which is a constant. We kind of grouped that and got it outside for convenience. And well, because all of this it's a numerical number, we can get it. And here we have the matrix. Of course, we only take into account 1 to 6i, because, well, we can see how 2 starts falling into a diagonal, then minus 1, then minus 1, and the other values are just 0. So we end up with a three-diagonal matrix, a symmetric matrix, and a square matrix. All into a matrix notation, we get this. And if we solve that, we get eigenvalues, and those eigenvalues account for our energy electron levels, and that's the beauty of this. Of course, those eigenvalues, we already have the analytical approach, so we can kind of compare and contrast to see if we did everything right. We will do this, of course, in an analytical method and also in MATLAB, so that we can kind of account for both approaches and use linear algebra, which is the main objective and goal of this project, rather exam, let's say. So let's go now into the main thing we have to get. So first we have to choose our target color, which in this case will be red, as we already said, for convenience and to keep things as real as possible. So we have the following value of the band gap of gallium arsenic into here. It's given in EV. And well, we also have the emission energy formula estimation, where it is important to just know that, of course, this is the energy in the wavelength. This is the energy in the band gap. This is the energy in the first electron energy level. And this term right here is the first heavy hole energy level. We also are given that the mass will only be 0.067 of the whole mass. And we also have the MHH, which is the mass in the first heavy hole energy level. We also have this different kind of approximations will be useful in order for us to solve this emission energy estimation formula. So let's go through that. And afterwards, we will end up with this, which is the analytical approach in order to get the energy electron values, which we already got in like our lectures. But if we solve for A, that's actually really interesting to see. If we solve for A in there, well, we get this formula and we can approximate and get as close as possible to the real quantum well width, which is kind of given by A. So let us see this in our document. So first, we end up with this wavelength related photon energy formula. It's important to see that we are already given the lambda, which we are missing in order to perform the following calculations. But it's also important to see that we are being given this in nanometers, and here we have micrometers. So it's first important to convert those nanometers into micrometers so that we can cancel this when we are doing the unit evaluation, and we will end up with EV, which matches this EV right here. So let us go through that. It's important to know, of course, all of these values, which are already given in our instructions. And we also have the formulas which we were talking about just a second ago. So with the values we are given, we can calculate these right here. Of course, we already converted the nanometers to micrometers, and we end up with this, which, of course, matches the given value. So that's the first thing we have to kind of check, and we did it right. So we are going into the correct path, the right path. And well, of course, it's just as close as possible. So we end up not with kind of an equivalence, but it's close enough so we can continue. Now, using these values, which we already were given in the instructions, which is the band gap energy and the energy in the first heavy hole energy level, we can solve for the first energy electron level in another way, which we will kind of try to prove in the analytical approach we were already given. So, well, this is basically just replacing values and doing some basic algebra, and we end up with this. Now, let's try to compute the well width A, which is kind of one of the main approaches and one of the main things we have to get. And also we can prove this value into the analytical approach, which was what we were saying just a second ago. So here we have this with already the values plugged in. But well, let's also remember that from this formula, we can solve for A, which is kind of the main target variable we are having into this because all the other values, we already have them. Like we have the reduced Planck constant, we just have to square it. Of course, pi is already kind of trivial. We have the mass, but we have to remember that it's not the complete mass. So here we have the mass of an electron. And well, only have to compute for the 0.067% kind of the mass. So here we also have an important thing to just mention because this energy level value, we were getting it in EV, but so that we can cancel these joules, of course, we have to convert them to joules. So using just kind of course, the value already for 1 joule equal to blah, blah, blah EV, we get this and we plug it in right there. So after performing just the calculation and substituting using our calculator, we end up with A in meters, but it's times 10 to the minus 9. So if we use our nearly forgotten knowledge of units, we can see and detect that we are talking about nanometers, which, as seen in our lectures, is kind of the normal thing to have in a quantum well width problem. So we're going into the right path. Now let's try to get the first energy electron level in this analytical approach. So we are just kind of using the value of A, which we already got, we can substitute and we will get this right here. It's important to see that, well, as expected and just as kind of a signal or, yeah, let's say a sign that we are doing things right. Well, the value obtained using the first kind of method we were given in the instructions was this. And the value obtained after getting A and using the analytical approach, which we derived into our lectures, is this. And we can see that they are close enough. So we are going into the right path. Now let's just kind of language, programming language, in order to see if we did this. Using the already gotten MATLAB that we used in our final project, we can see all that, well, it's a function that asks for A, the number of n, and the mass, which in this case we know it's 0.067 times the actual mass of an electron, which is real here. We have also h bar, which is the Planck constant, which, as we were talking in the beginning, is just a numerical value. So we have it into here. And this Q, it's actually also important because, well, we have to convert that final value into EV. So after going through the construction of the tridiagonal matrix and using the value for delta X for um, the mass, also the Planck constant, sorry, and telling our command window as seen in here, what are the values that we are using. This is the A in meters. This is the number of N. Of course, we're using 200 because as seen in the project, if we increase and we make the value of N bigger, it's going to be just as we saw in Euler methods. In Euler, yeah, with Euler, just Euler, sorry. We can see that with larger values of n, we actually are getting closer to the real value, as this is kind of only an approximation, of course. And we have the percentage of the mass which we are using, and our function just accounts for that using, of course, the value of the mass of the electron completely. Here we are telling our function we only want the first energy electron level, and this is the answer we get already in EV, not joules, because our function already changes those EVs into, sorry, changes those joules into EVs, and we get this. So we can see that it matches the values we did obtaining the approach given into the instructions of the exam and the analytical approach used in our lectures. So, well, that just tells us that we did everything right. And our MATLAB code works because, well, we already proved it in an analytical way. And, well, that's basically it. So our final results then are the following. And we can see that this was already given. Let us see the energy of the related photon energy was already here in EV. But well, using the approach, we see that it's close enough, so we are actually doing good. Then this was already given. This was not given, but we had three different ways to solve for that and account for that. The analytical method kind of presented into our instructions, the analytical method presented in the class, and also with MATLAB. And well, here we also have A, which we derived with the formula given after solving for A in the first energy electron level formula. And that's the beauty of linear algebra, because, well, of course we can do everything in an analytical way, but that's rather boring, because, well, we are not applying our knowledge into computing, into programming, into numbers, numerical methods, whatever. So we can use linear algebra in order to account for all of those processes and kind of make them easier. And that's the thing we are doing in here. So, well, our role in the semiconductor company ends here. Now we have, of course, to give this information to following teams: the epitaxy team, the fabrication team, the characterization team, and the marketing team. But, well, basically, our job is done right here. And we are actually, and finally, kind of, let's say, glad with our results because, well, they match different approaches and they are actually being used in a realistic way. And we know that our design is possible. So this is it. I hope you enjoyed and we will see each other next time. Bye bye.